So to some extent, that answered the question why in our derivation, it seems like we are doing quite classical calculations to a quantum system. So here is because the observable that we are evaluating, basically the Hamiltonian, plays a special role in the definition of the density operator. Okay, so if we try to think about if we want to evaluate the expectation value of an operator O, for example, if O is some kind of total position coordinates, then when we try to evaluate the expectation value of O, we will need to, in principle, do this summation. But now, this expectation value is non-trivial, then we really need to include the information about the wave function to really evaluate the expectation value of this particular observable O. Okay, so that's one caveat that I should explain a bit more in detail in order to make the derivations makes more sense. Okay, so after that we discussed the Fermi and Bose statistics. So that's the subtlety that is related to the wave functions property. Okay, so this is the part that we have discussed extensively during the last lecture. So the most important concept is that in 3 dimensions we have fermions and bosons. Okay, and the important difference is the wave function. For fermions, the wave function is anti-symmetrized. And for bosons, the wave function is symmetrized. Okay, and sometimes this anti-symmetrized wave function can be expressed as determinant, and that's called the Slater determinant. Okay, so this difference of the wave function leads to the Pauli exclusive effect, or the Pauli exclusion principle. Fermions. For bosons, they don't have such a constraint, so all the bosonic particle can stay in the same quantum states. So from there, we basically try to construct the canonical ensemble for fermions and bosons. and it can be written as this for n particles. We basically have our partition function described by this. So here is the Kronecker delta function that it is equal to 1 only when the summation of mpj alpha is equal to the total particle number n. Okay. And of course, for a canonical ensemble, we need to have the Boltzmann factor. And for free particles, the Boltzmann factor is related to the total kinetic energy, which can be considered to be the summation over different momentum modes over pj, and for each mode there's a m particles occupied there. So that's basically the partition function. So let me try to be specific about each terms. The sum over alpha is sum over the internal degrees of freedom, such as spins. Okay, and this summation over all the occupation number can be understood like this. So maybe you have a configuration with one spin up particle sitting at momentum p naught and one spin down particle sitting at momentum p naught, and maybe a -2 spin up particle sitting at momentum p1, and the rest of the states are not occupied. So this is a valid configuration because if you add up all the particle numbers, one at p naught with spin up, one at p naught at spin down, and n-2 of them at p1 spin up, the total particle number sum up to be n. So that's a valid configuration. But in principle, when you sum over all the possible occupation numbers, because at this moment we didn't impose any constraint, we can have actually this type of configurations where maybe there are, I don't know, wait a second, one additional particle at momentum p1 but spin down. Okay, so this configuration is not allowed because the total particle number add up to n+1, not n. So in order to rule out this type of configurations, we include this Kronecker delta function to constrain the sum. So at this moment, you should see or you should be careful about several things. So one thing is, let me try to describe it here. So here, J is the index of the state. Okay. It is not the index of a particle. The reason is simple, because we are discussing about indistinguishable identical particles. So this index J actually count the modes, not the particles. And because we switch to this representation, actually we are facing a non-trivial constraint. The constraint of total particle number n. So the evaluation of this Zn is actually not easy, because you need to deal with this non-trivial constraint. Okay, so we can try to ask ourselves where this non-trivial constraint came from. It actually came from the fact that we switched the representation of my my index for the particle 1 to n to the occupation representation. Where J labels the state. Okay. And the point that we want to switch to this occupation number representation is exactly because we want to consider the effect of quantum statistics. So I will pause here and take a 10 minutes break. And if you have any questions, you can ask me. See you after 10 minutes. Okay, so let's continue our discussion. So as I mentioned, the reason that we switch to this occupation representation is because we want to include in the effects of quantum statistics. However, by doing that, actually we face a non-trivial constraint. So that's the point where grand canonical ensemble is useful, because it can help us to relax the fixed particle number constraint. So let's see how it is done. Okay. So the standard process to construct the grand canonical partition function is to sum over all the possible particle numbers and times the fixed particle number partition function times a factor that is related to the chemical potential. Okay, so now when we sum over the possible total particle number n and combine that with the constraint, we will find we can simply replace the n here by the summation over occupation number at different modes and different polarization. That is, we basically remove the non-trivial constraint of the total particle number, and we need to sum this expression. Okay, so at this moment, we are going to use another very important assumption that we are dealing with non-interacting systems. And the partition function can be factorized into products over different modes, where on each mode it is described by a summation of all the possible occupation number for this particular mode. Okay, so this infinite summation, or maybe finite summation for fermion, is the operator that we are is the function that we are going to express as zeta eta as a function of the energy epsilon of Pj minus the chemical potential mu. Okay. So what we have done here is that we basically relax the fixed total particle number constraint by going to the grand canonical ensemble and factorize the partition function. Since we are studying non-interacting systems. Okay. And what does it give us? It basically allows us to study the quantum statistics of different modes. That's good because our problem is now simplified by this procedure to analyze the quantum statistics for a particular mode. Okay. So are there any questions right now? Okay. So now we are going to see why it is important when we reduce our problem to quantum statistics of each mode. Because basically we can incorporate the Pauli exclusive principle easily. So for fermions, because of the Pauli exclusive principle, this function zeta of eta, zeta eta of epsilon pj minus mu simply contains two terms, because this occupation n can only be 0 or 1. So when it is 0, then basically this exponential factor is 0, and it will contribute a term 1. And when it is 1, it will just give us a simple Boltzmann factor. Okay, because mpj equal to 0 or 1. And for bosons, mpj goes from 0, 1 to infinite. So what we are facing is actually, this should be fermion. This zeta function for the boson, for bosonic mode, actually there should be an alpha somewhere, because we have in the most general case the energy could depend on internal degrees of freedom, but now it seems like it is not very useful, but let's just keep it. Okay, and because this infinite series can be solved when this ratio is smaller than 1, and the result will be this. Okay, so because of this two expression, we can use parameter eta, which is +1 for boson and -1 for fermions, to re-express this zeta eta as this. Okay, and here I'm using the convention that this eta is used for symmetric wave function when it is positive, and if it is negative, it is or it corresponds to the anti-symmetric. wave function. Okay. So if we take the natural log of this grand canonical partition function, as we have learned before, it should correspond to the thermodynamic potential omega. And once we turn this, once we take the log, this product will becomes the summation. And the log of this zeta function can be interpreted as the omega potential for each mode. That is described by Pj and alpha. Okay. So at this moment, we didn't really specify what is the function form of the energy as a function of Pj. It can be quadratic in momentum Pj, or it can be cubic. It can be just anything. But for the simple system where we are considered free particle, we will put the quadratic dependence inside. But usually we can make a first level simplification, that is, the energy is independent of the internal degrees of freedom alpha. Okay, so if we make this simplification, that leads to the fact that summation over the internal degrees of freedom is just a trivial sum. You just ask how many internal degrees of freedom are there. And for system with spin S, usually these internal degrees of freedom will have a total 2s plus 1 choices. So if we make this a further assumption, we can simplify this summation alpha, and the expression of the natural log of the grand canonical partition function simplifies to okay, and this thing is basically the omega potential divided by kBt. Okay, so once we know the omega potential, it is very tempting to evaluate what's the possible occupation number of our system, and basically one can derive that, but by taking the derivative of the omega potential at this mode Pj with respect to the chemical potential. And you can simply insert the expression here, the natural log of this zeta eta function, and this zeta eta function has a general expression that is shown here. Then once you take the derivative, what you will find is this. And after you simplify them by cancel some of the factors, and you will realize the occupation number, or the expectation value of the occupation number for each mode will have this function form. Okay, and here eta is +1 for bosons and -1 for fermions. And they are sometimes called the Bose-Einstein distribution and the Fermi-Dirac distribution. So this result is quite general because, as I mentioned, I didn't specify what is epsilon of P. So whenever we got some general expression, it is usually useful to think about what are the possible simplest application. So if we assume that we are thinking about a free particle, that means that we can specify the energy expression epsilon of Pj to be Pj squared divided by 2m. And we can ask under this form of the energy, what results will we get? Okay. So let's see. So let's start from this expression. Okay. And let's keep the eta as the parameter, and we just assume that eta is independent. The energy is independent of the polarization or the internal degrees of freedom alpha. Then we will have the natural log of grand canonical partition function to be 2s plus 1. This vector came from the summation over alpha times L divided by h to the cube integration over the momentum. This is coming from the summation over momentum to integral over momentum. Okay, and we can take the natural log of this zeta function, and we will have a minus eta vector drop out, and here I will express the result using the fugacity. Okay, so this is the fugacity. So as usual, we want to perform this integral at the isotropic limit. So we will have 2s plus 1 L divided by h to the cube. That's the constants that we had. And 4 pi, which came from the angular integral, and minus eta coming from the constant inside the integral. And then we have okay, so here should be something related to your homework. You can just do a simple change of variable by let p equal to square root of 2m kbt times p tilde, and perform this integration using the infinite series expression for natural log 1 plus x. Then you will find this expression. Okay, so the question is how to evaluate this integral, and it turns out that this integral is closely related to the Gaussian integral, as always. Okay, the reason of this 1/2 factor is because this function is an even function, and it must converge. And this expression can be considered as a differentiation with respect to n when you have a Gaussian integral that looks like this. So eventually you'll find this result to be equal to this expression, and if you plug that back to this integral, eventually you got the final result that the grand canonical ensemble for bosons and fermions can be expressed like this. In 3 dimensions. And this thing is basically the polylog function. Oops. And if we try to evaluate the expectation value of the total particle number n, because at this moment n can be fluctuating in the grand canonical ensemble, it should be expressed by this. And if you do the differentiation carefully, you'll find that it's equal to and here we use the property that the differentiation of polylog function should be another polylog function with the coefficient alpha changes by 1. Okay. So are there any questions so far? Okay, so if not, so we just got to important relation that this thing is actually the classical value of the total particle number n. So we got 2 equations. One is about the natural log of the grand canonical, which is minus the omega potential divided by kb by kbt, and the other is the constraint related to the total particle number. So as we can see, this polylog function is a function of a geometric series of a bunch of z to the power n divided by n to some alpha power. So one of the limit is when z is much smaller than 1, that this polylog function phi alpha of eta z can be simplified to be eta z. The reason is all the higher terms will decay faster compared with the first term. So if we do this replacement, what we found is that the total particle number n at this limit should be equal to eta times 2s plus 1 times L divided by lambda to the cube and times eta z. And no matter it is for boson or fermion, at this limit, the dependence of eta basically drops out. So one can have a approximate value of z to be n times c to the cube times 2s plus 1. Is it right? No, it's not right. Something went wrong because I should have 2s plus 1 here. Okay. So if we define this quantity n times lambda divided by L to the cube to be c, we have z basically proportional to c, and the proportional factor is something that's of order 1. Okay. By the way, I think at this moment it should be clear that this lambda is related to the de Broglie thermal wavelength. Okay. So at this limit, we can invert the relation of z and n and get the conclusion that z should be proportional with some coefficient or some dimensionless parameter c. And basically, this c has a physical meaning that it is the ratio between the volume occupied by each particle and the volume occupied by the length scale of the de Broglie thermal wavelength lambda. Okay. So here we want to check the self-consistency. So when we have z to be much smaller than 1, we derive the relation that z is proportional with c. And at this limit, we can also see one thing, that basically the natural log of z going canonical, as we discussed, should be related to and wait a second. Somehow I feel I missed a minus sign somewhere. No, I don't think I missed anything, because omega is minus PV. So at this limit, actually, we found the state equation actually is the ideal gas equation. Okay, so when we are at this limit, we are basically at the ideal gas limit. And at the ideal gas limit, we know that this ratio c is automatically much smaller than 1. So this is internal self-consistency check, because when z is much smaller than 1, it also implies z is much smaller than 1, which is the assumption that we start with. So we reach some kind of internal consistency when we try to include the energy of the system as the free energy, as the free particles kinetic energy. Okay, so now we are going to leave the classical limit, where we know the system is basically an ideal gas model. The first limit that we want to discuss is when the Fermi statistics is really important. So let's try to start with the concept of Fermi C. Okay, so now I'm trying to think about the quantum limit and consider the system is formed by fermions. And as I mentioned, the most important structure for this derivation is that we basically simplify the analysis to a analysis of quantum statistics of a single mode. And for fermion, basically they can be only occupation 0 or 1. And that feature actually is expressed in this Fermi-Dirac distribution function. So let's try to take a look about the Fermi-Dirac distribution function. So let's say we have an F, which is a function of the energy epsilon. And it is a function that looks like this. Okay, so the first thing we should notice is that this exponential function must be something that's greater than 0. Okay, so which means that this Fermi-Dirac distribution function must be smaller than 1 for all the possible energy. Okay, that's the first thing. And the second thing is that at the quantum limit, where we consider temperature is very low, that means the factor, the parameter beta is sent to infinite. So at this limit, actually this distribution function has a very spatial structure that is when the energy is greater than the chemical potential, basically this exponential term diverges. So the value of NF as a function of energy is very small. Basically, it dropped to 0 very quickly. Okay, and whenever it is smaller than when the energy is smaller than the chemical potential, that means that this exponential factor drops to 0 exponentially fast, and the filling or the Fermi-Dirac distribution saturates at the value 1 very quickly. Okay, so this is the behavior of the Fermi-Dirac distribution at t equal to 0. And it is interesting to ask what happens if t is not equal to 0. So what's going to happen is that this distribution function will be rounded. So we will have something that might look like this. Okay, so this is like the t not equal to 0 case. So the region where the states will be influenced is within the energy window of KBT. And we can notice that outside this window, basically, the states are still exponentially close to the saturation value. So those states are actually not really active when we try to change the temperature. So here are several important questions or important energy scale. At the temperature equal to 0, the highest energy that the state is filled or is basically the chemical potential at T equal to 0 is what people called the Fermi energy. Okay, and this energy scale is only defined at the is only defined at the 0 temperature limit. So how to calculate the Fermi energy? The expression is actually also simple. In general, the total particle number should be calculated using this formalism. Okay, so here is the G of E is the density of states per volume. That's the reason why we need to multiply a volume factor outside the integral. So basically, this integral counts how many moles are there in the system, and for each moles, it is occupied by this occupation number given by the Fermi-Dirac distribution. This formalism is true for all temperature. However, at T equals to 0, this Fermi-Dirac distribution becomes the step function that we shown in the screen. So what that means is that this integral at T equal to 0 can be significantly simplified. So once you perform this integral, it will be a function of Fermi energy. And if you invert this relation, you will get the relation between the Fermi energy as a function of particle number. And the density of states, G, basically depends on what kind of Hamiltonian you have. You could have free particle system, or you can have a simple harmonic oscillator. So that depends on the detail of the system. Okay. So one of the most important concepts that we want to study is basically the specific heat for a fermionic system.